Hello students, so here in this class we are going to solve a problem for a beam. Okay, so you going to use direct stiffness method. Okay, so let's analyze the beam. So let's move to a question. There is a support A, support B, so a continuous beam is there. So let's label the beam as A, B, C. This is B, this is C, and B to C there is a UDL. Okay, there is a UDL of 24 kilonewton per meter. 24 kilonewton per meter. Okay, and it has a moment of 40 kilonewton per 40 kilonewton meter, and there is one moment of 30 kilonewton meter. Okay, there is also one point load acting. Okay, one point load acting at a distance of 4 meter from left end, that is 100 kilonewton. So this is 100 kilonewton, and total length of the bar, this particular end, it is 8 meter, this is 8 meter, this is 10 meter. Okay, and this particular distance, it is 4 meter. This is 4 meter. There is one more thing, that I is not same. Okay, so this part of the beam, it is having 3 EI, and this part of the beam, it is having 2 EI. Okay, and there is also a rotation here, moment here, 20 kilonewton meter. Okay, so this is our question. Now let us consider the nodes. Okay, let's decide the nodes. So for this particular, let us consider the nodes at ABC. Okay, let us consider. So nodes are considered as, or let us consider nodes as A, at A, B and C. So what is the degree of freedom? So degree of freedom is 1, 2, 3. Okay, so let us write down degree of freedom. Degree of freedom is equal to 3. Okay, 1, 2, 3. So let's write down what it is: theta A, theta B, theta C. So these are the degrees of freedom. So let's show in a diagram. Let's show the coordinates in direction of degree of freedom. Okay, so let's draw again once more the same beam. Okay, so we know that this is a continuous beam, and simply support continuous beam is there, so hence supports are there. So here we are showing coordinates in direction of degree of freedom. Okay, we are showing the coordinates in direction of degree of freedom. So this is coordinates in direction of. Okay, so once we are done with this, now let us write down displacement matrix. Okay, let's write down displacement matrix. So how do we write displacement matrix? Displacement matrix with respect to degree of freedom. Therefore, displacement matrix with respect to degree of freedom, so that is equal to delta, and it is shown as theta A, theta B, theta C. Okay, that is at the place delta 1, delta 2, delta 3. Delta 1, delta 2, delta 3. Okay, corresponding to theta 1, theta 2, theta 3. Okay, now let us consider a member Ij with nodes at I and J. So let us consider a member Ij at I and J. Okay, so let us show it in a diagram. So this, let us consider this member. Here it is I and here it is J. Okay, so let us write down the rotation theta I, and then there is rotation theta j, and also show the displacement Vi and Vj, and it is having a length L and EI. Okay, so these are the element coordinates. These are the element coordinates. So we know the element stiffness matrix. Okay, element stiffness matrix. We know how to write element stiffness matrix for above member. Element stiffness matrix for member Ij. So we have also seen this in previous class, right? So that is small k Ij is equal to Ei by L cube, Ei by L cube. Then write down the matrix, that is 12 minus 6L minus 12 minus 6L minus 6L 4L square 6L 12 square minus 12 6L 12 6L minus 6L 2L square 6L 4L square. Okay, so you have to remember this. So the first row corresponds to Vi, then this is theta I, Vj, theta j. Similarly, this is corresponds to Vi, theta I, Vj, theta j. Okay, so this is our matrix. Now let us substitute all the values over here. Okay, so Ei by L cube. So now just see here for member AB. Okay, for member AB it is 3 Ei by L cube, right? 3 Ei by L is 10. So make it 3 for member AB. Okay, let us find out what is the matrix for AB. So 3 Ei by 10 cube and write down all the corresponding values. Okay, so what is it? 12 minus 60, 12 minus 6 into L. Okay, 6 into L, L is how much? 10. So 60, then again minus 12 minus 60 minus 60, 400. This is 60, then it is 200, then it is minus 12, this is 60, this is 12, this is 60, this is minus 60, this is 200, 60 and 400. Okay, so this is our stiffness matrix. So with this, let us see when you multiply. Okay, with this, when you substitute all the values, EI value and 10 cube, so everything when we substitute, so let's see what is the final matrix we are getting. Okay, so we get, you also do the calculation and I am writing what answers I have got. Okay, so it is EI. So I am just writing this just for the reference, that this is VA theta A, VB theta B. Okay, so I am getting this first row as 0.036 minus 0.18 minus 0.036 minus 0.18 minus 0.18 1.2 0.18 0.6 minus 0.036 0.18 0.036 0.18 minus 0.18 0.6 0.18 1.2. Okay, so this is corresponding to VA theta A, VB theta B. Okay, so this is our answer for K of AB. Similarly, you have to do it for K of BC. Okay, so for K of BC, how we will write the K of BC? Our stiffness matrix will be 2 EI by L cube, and their span is 8 meter. Okay, so here we will write 2 EI by L cube, and the inner values will be 12 minus 48. Why it is 48? Because it is 6 into L, and L is nothing but 8 meters. So 8 are 48. Okay, so 12 minus 48. minus 12 minus 48, minus 48 256, 48 128, minus 12 48 12 48, minus 48 128, 48 256. Okay students, so this is the matrix we have got, and once you substitute all the values, okay, so then our answer in terms of EI, okay, is the final answer is 0.04688 minus 0.1875 minus 0.04688 minus 0.1875. So this is the first row. The next is minus 0.1875, 1, then it is 0.1875, it is 0.5, minus 0.04688, 0.1875, 0.04688, 0.1875, minus 0.01875, 0.5, 0.1875 and 1. Okay, so our answer is, this is for again VB, theta B, VC, theta C. Okay, so this is for, these answers are for, this column is for VB, theta B, VC, theta C, VB, theta B, VC, theta C. Okay, so displacement, rotation, displacement, rotation. Okay, so stiffness matrix with respect to, now let's see the stiffness matrix with respect to degree of freedom. So how do we show it? We show it as K delta, and it is obtained by superimposing individual element stiffness members. Okay, so stiffness matrix with respect to degree of freedom, with respect to degree of freedom, means it is K of delta. Okay, is obtained by, it is obtained by superimposing individual element stiffness matrix, individual element stiffness matrix. So in this case we can write K as, K we can write it as, what we will write? So we will write the value, we need to write the value of theta A, theta B, theta C. Okay, theta A, theta B, theta C. So it is 1.2, 0.60, and this is 0.6, and what, how much it will be? 1.2 plus 1. Okay, so if you see theta B, it is 1.2 plus 1, so it is 2.2. This is 0.5. Okay, theta C corresponding, just see here, for theta A it is 1.2. okay, for theta A it is 1.2. Then for theta B it is 0.6, that's what we have written here, and theta C it is 0. Okay, but for the next column, next row, theta A is 0.6 and theta B. Okay, so next is, it is 0.6 for theta A, 0.6, and theta B is 2.2. So this 2.2 is because of 1.2 plus 1. So that's how we get it here as 2.2. Okay, and then here it is 0, 0.5 and 1. Okay, so this is our stiffness matrix after superimposing. So 1.2, 0.6, 0. So this is our, when we write in terms of, we can write, after getting the K value, we know that delta is equal to K inverse of delta P of delta. Okay, we knew this formula. So whereas P delta, okay, P delta is a force matrix with respect to, this is force matrix with respect to degree of freedom, with respect to degree of freedom. Okay, so we can write P of delta is equal to P of equivalent delta plus P of E delta. So we will, this equation we have already seen in a theory. Okay, so after this we have to do the equivalent joint load. Okay, calculation of equivalent joint load, calculation of equivalent joint load. So we write it in shortcut EQJL. Okay, so direct stiffness method, it for this EQJL, for in direct stiffness method we always need to calculate the reactions. So let us consider a part AB. Okay, AB and BC, two parts are there. Now let us redraw the beam. So if you have forgot, AB and BC. Okay, so we'll show AB as a fixed member and again we'll show BC as a fixed member. So let's draw two beams here. We have to find out the fixed end moments. So let's show the fixity. So this is first part of the beam and then I'll draw nearby the second part of the beam. So here this particular, we have to calculate what is the fixed moment. We also need to calculate what are the reactions. Okay, so here how much, 100 kilonewton load is acting. This is 4 meter, this is 6 meter, and for this there is a UDL. Okay, so for UDL it is 24 kilonewton per meter. Okay, so for UDL what will be the fixed end formula? Who remembers it? It is WL square by 12. It is WL square by 12. Okay, so when you substitute value, W is 24, L is 8 meter in this case by 12, so we get the answer as 128 kilonewton meter. Okay, at both the sides, 128 kilonewton meter. We also need to find out what is the vertical reaction here. Okay, so when you calculate vertical reactions, and for this formula WAB square by L square. Okay, so I'm not here spending time now. This is in so many questions we know that what is the fixed end moments. Okay, so the value of fixed end moments anyway are just WAB square by L square. When you substitute, you get the answer as 144 here, and here WA square B by L square. So here we get the WA square B by L square. So we get the answer as 96 over here. Okay, so once you get the moment, then we will calculate the reactions. So at this point our reaction is, I'm just writing with a different color. So it is 64.8 and here reaction is 35.2 kilonewton and here reaction is 96 kilonewton and 96 kilonewton. Okay, so these are the reactions. So how we are going to show a equivalent joint load? Okay, so equivalent joint load we can show as, again redraw these two members. So here we are going to show moment 144, in opposite direction moment we are showing it is 96 and the reactions also in opposite direction, 64.8 and this is 35.2. Again here 128 kilonewton meter and the load like this 96. So here also it is 96 and the moment is 128 kilonewton meter. Okay, so with this now let us write down what is P equivalent. Okay, so what is the P equivalent? So P equivalent is equal to, so write down this moment now, 144. Okay, here at this point it is 144. So write down 144. Then we have to add up minus 96 plus 128. Okay, so here you see the two moments. So we can write minus 96. Okay, sorry, here we have to see. So minus 96 anti-clockwise negative plus 128. So we get the answer as 32 here in this row. And the last is 128 minus 128. Okay, so here we can see that directions are, so the first direction is clockwise second is also clockwise positive answer we are getting, and third is minus 128 we are getting. Okay, so we can name them as 1 2 3, three answers we got here. Okay, I mean these are the three answers we got here. Now let us calculate what is PC. Okay, P equivalent, sorry. So this is P equivalent we got, and our formula is PE delta, right? So the next PE we have to find out. So PE is equal to minus 30, minus 20 and plus 40. So this we will see only through our problem. Okay, 30, 20 and 40. Okay, so these are the values we have written here. Okay, minus 30, minus 20, minus 40, plus 40. Now let us find out the total. So we will simply add them up. Okay, this plus this. So let's write down, that is P delta is equal to, add these two columns, 144, 32 minus 128 plus minus 30 minus 20 plus 40. Okay, so this gives us answer P delta is equal to 114, 12 minus 88. Okay, so once we get P delta, then the K inverse, okay, K inverse delta is equal to 1 by EI 0.98485 minus 0.30303, this is answer, and 0.151.52, sorry, 151.52. There is some slight mistake here. It is point, let me just correct, there is some small calculation mistake, 0.15152. Okay, and this is again minus 0.30303, then 0.60601, then again here minus 0.30303, then here again 0.15152 minus 0.30303, and it is 1.15152. Okay, so once you get the K inverse value, then substitute all in formula, that delta is equal to K inverse, K delta inverse into P of delta. Okay, so delta answer we get it as 1 by EI when we multiply above matrix. Okay, so above matrix, again I'm not just rewriting it, so it is the same matrix we have to write into this column. So that is 114, 12 minus 88. Okay, so when we do this, finally we get the delta as delta is equal to 1 by EI 95.30303 minus 0.60606 minus 87.69697. Okay, so this is equal to delta 1, delta 2, delta 3, right? And it is at theta A, theta B, theta C, that is the rotation, right? If you just check it. So now we know that EI value is given as, EI is given as 30,000 kilonewton meter square. Okay, so displacements, what are the displacements? So displacements are rotation at A. Okay, rotation at A. So what is the value at A? That is 95 point. So that is theta A is equal to 95.30303 divided by EI. EI value we will substitute. So we get the answer as 0.182 degree. Okay, so this answer is in radian and this is in degree. So similarly, rotation. What is the rotation at B? So rotation at B is nothing but theta B. Okay, so theta B is equal to 0.60606 by EI. So we get, this is a in radians. Okay, this is also in radians. So final answer is 0.001157 degree. Okay, and the rotation at C. Rotation at C, that is theta C, is equal to 87.6969 by EI. Okay, so this is 0.16748 degree. Okay, so once we get the rotation, then calculation of member and forces in direction of element coordinates we need to calculate. Okay, so calculation of member and forces, calculation of member and forces in direction of element coordinates. So we have to write P of ij. So we know the force. Okay, we have the force P of ij is equal to K of ij delta of ij minus P equivalent. So here now let us start this calculation. So let us consider AB. Consider member AB. So for AB we know VA, MA, VB, MB. Okay, so we know VA which is in upper direction, MA, VA, MA, VB, it is again in upper direction, and MB, right? So which is equal to EI, and then write down rotation minus 0.18, 1.2, 0.18, 0.6. So this is for theta A, and for theta B we can write minus 0.18, 0.6, 0.18, 1.2 into 1 by EI 95.30303 minus 0.60606 theta A theta B minus, okay, so these are for theta A theta B. Okay, so minus what is the next? P equivalent, right? So that is minus 64.8, 144 minus 35.2 minus 92. So this column how we will get? We have to see only equivalent joint load. Okay, so then we'll get this column. So once you add this up, so we get the answer as, final answer we get it as, you know, this EI will get cancelled. So final answer is 47.75 minus 30, 52.246, 152.457. Okay, so this is all for member AB. Now let us consider member BC. Okay, BC, consider member BC. So for BC, again you have to write BB, MB, VC and MC. It is equal to EI is equal EI into, then write down the values theta A, theta B, theta C. So it is minus 0.1875, 1, 0.1875, 0.5, minus 0.1875, 0.5, 0.1875, 1, okay, into 1 by EI, 0.60606 minus 87.69697. Okay, so we already have these values, we are simply writing them. Okay, so theta B corresponding to theta B theta C, then minus 96, 128, minus 96, 128. So once we are done with this calculation, we get the answer as 112.557 minus 172.455, it is 79.43443 and 40. So this is our answer. So once we are done with this, okay, VB, MB, VC, MC. So once we are done with the calculation, then we can simply reflect these values on the particular beam, and then we can calculate shear force and bending moment diagram. So this is a lengthy question, but once we remember the step, then it is easy to solve. Okay, so students, hope I want you to go through the question once or twice, and then you will understand the steps. So you need more practice to remember it. Okay, so thanks for listening the lecture. Thank you.